Great. So my name is Robin Dalmassen from the Reservoir Characterization Research Laboratory at the University of Texas Austin Bureau of Economic Geology. And I want to extend my thanks to my co-authors from Geophysical Insights, Alvaro Chavez and Thomas Chaparro. So this presentation will be on the Kingdom Abo field and data set. The Kingdom Abo field is located in the Permian Basin of West Texas, and there's an increased interest in these Leonardian shallow water platform reservoirs, mainly because of the increased activity related to saltwater disposal and CCUS, as you already could see from from Tarek's presentation. Big interest in unconventional carbonate reservoirs in the Permian Basin that our research group is encountering based upon the interest of the sponsor companies. The Kingdom Abo field, the lithology consists almost completely of dolomite, and the 3D seismic surveys is more than 35 years old and is of a fairly low resolution. We have some unpublished previous seismic acoustic impedance inversion work, which was a very time-consuming process and ultimately inconclusive. So we decided to revisit this challenging field using the Paradise machine learning lithofacies prediction approach. So our big question for this presentation is: can Paradise machine learning-based lithology prediction help in delineating reservoirs in areas with challenging petrophysics and seismic qualities? So in the depositional model that you see here in the upper left-hand corner, I'll turn my laser pointer on over there, you can see that we have several time stratigraphic units which comprise cliniform deposits that consist of the inner shelf, the shelf crest, and the shelf margin, as well as slope facies. And we have about 3 time transgressive lithostratigraphic units. And we noticed that the system progrades basinward, yet we have a dipping main payzone highlighted here in the depositional model, which is highlighted by the low amplitude signal here in the seismic cross section. That's the AA north to south cross section shown on this index map right here. So some of the seismic resolution challenges that we faced is that it was, of course, acquired in the 90s. We have a dominant frequency about 30 hertz and useful bandwidth up to about 70 hertz. The seismic data allows for good well-to-seismic ties, as the question was brought up already, and Alvaro emphasized it very thoroughly. It's an absolutely critical step in the proper execution and application of the Paradise lithofacies workflow. The challenge with the lower frequency content is that we have difficulty resolving bed thicknesses below approximately 20 meters, which is very typical of most mid-90s industry surveys. So the dominant rock type, as I mentioned, is dolomite, and that makes for a kind of a challenging application of this of the Paradise lithofacies prediction. We have done some other applications of the Paradise lithofacies prediction in carbonates, and I'd like to refer you to some of the presentations that we have done that are on the Bureau of Economic Geology YouTube website, in which we have applied Paradise successfully in using more recent vintage seismic. But this was a real challenge, older seismic as well as a very challenging petrophysics. So we thought it was a good test for this sort of application. So the important workflow elements, some of which precede the application of the lithofacies prediction in Paradise, is we performed a petrophysical multi-mineral inversion using Schlumberger Techlog and Dynamics software. This resulted in the calculation of mineral and fluid compositions for about 113 wells in the field. We interpreted approximately 300 seismic horizons using both the PaleoScan and Petrel software using a geomorphologically oriented interpretation workflow. And then using those 300 seismic horizons at very high resolutions, we built three-dimensional models in Petrel in both the time as well as the depth domain. And this model was approximately 14 million cells. Then the very important seismic well tie we did using the synthetic seismogram. We see some examples down here. You can judge the actual fit of the synthetic seismogram to our seismic, and we did that for as many wells for which we had high quality sonic and density data. And as Alvaro already mentioned, you really have to tie it down to the individual seismic sample in order to ensure that you get very good results in your machine learning-based lithofacies predictions. So the velocity information that we derived from that process was used to create a three-dimensional velocity model that we would then be able to use, that we then used in order to convert the 3D models from time to depth and vice versa. So then we calculated the 3D seismic attributes in Paradise, as the previous speakers explained in detail. We use principal component analysis to determine the most significant volumes that could be used to generate a self-organized maps, exactly like Tarek explained. And we also performed additional sensitivity analysis on multiple some self-organized map topology scenarios to determine the ideal number of neurons to be compared to the lithofacies curves. And then we use the Paradise machine learning tools like k-means clustering that Marwa was highlighted so well, as well as our own multi-mineral petrophysical results to determine a variety of lithofacies curves to be compared to the SOM volumes using the Paradise lithofacies prediction tool. So using a variety of statistical analysis tools that the previous two speakers touched upon, including Alvaro Silvestre's confusion matrix tools, we can determine the quality of the fit of the facies from the neurons to the facies from the wells. And in this particular case, running the confusion matrix tools quickly identified that our multi-mineral lithofacies curves, as well as our k-means derived lithofacies curves we had created, did not really produce very strong Kramer's V values. And that, of course, was a bit of a concern for us, right? And then, luckily, working with the Paradise team, we implemented a mutual information-based method, which considers target well logs when choosing which attributes to use in a self-organizing map. And some of these mutual information score methodologies are shown right here. Some of the challenging confusion matrices are shown here in the lower left-hand corner. Using the mutual information method, we were able to correct our workflow by identifying those well logs that obtained the highest mutual information scores, which we then used to improve our lithofacies curve, used to compare the SOM results created from the recommended 3D seismic attributes. And that resulted in this particular match between the lithology that we input to the prediction system compared to the SOM lithologies that we created using the recommended attributes from the mutual information workflow. So you can see from this particular well template that both the gamma ray as well as the photoelectric factor curve show the dominance of the dolomite. And then we show our porosity and water saturation, as well as our perforations in the field, the extracted seismic. Here are two scenarios for the two SOM topologies, and we can see the increased resolution we were able to obtain from a 15 by 15 SOM topology. So using the results of the Paradise lithofacies prediction workflow, we were able to then compare our input lithology to the predicted lithology from the SOM neurons in these last two tracks. And then we can, again, run the confusion matrix on that. And we see that we show a challenge of matching the subseismic resolution of the well lithology that you see in the lithology curve to the actual predicted SOM lithology. But what we can learn from the confusion matrix is that the tight dolomite lithology here, shown in purple, of course, as expected, has the highest prediction match, which you can see in the confusion matrix. The actual hydrocarbon-bearing dolomite has a high match with the predicted hydrocarbons from the SOM lithology, with very false positives, which of course is very encouraging. Right? Now, currently we still predict too much wet and hydrocarbon dolomite in general using the SOM lithology, as you can see from this track, right? But that we can attribute, of course, to the limited seismic neuron resolution. The encouraging aspect of this is that the depth ranges of the predicted wet and hydrocarbon dolomite match the depth ranges of the predicted SOM lithology quite well. So this is one of the ways in which we could use the similar tools that our previous speakers talked about, both the statistical tools as well as an optimized workflow to try to optimize the lithology curve in order to see if we could come up with a better prediction of the payzone distribution in the Kingdom Abo field. But then, of course, apart from the statistical tests to see how well the prediction matches the input lithology curves, of course, we wanted to come up with a better way to validate the overall results of the Paradise lithology prediction. So in order to do that, we decided to use approximately 12 horizontal wells, which we had kept as blind wells. So these wells were not used in the initial creation of the lithofacies prediction in Paradise. So we kept them completely separate. And then once we had created the three-dimensional SOM-based lithofacies prediction, we were then able to kind of compare the amplitude-oriented development strategy in the field to what we could learn from the lithofacies prediction strategy. So in order to do that, we extracted the low amplitude seismic along the horizontal well trajectory, which you can see in this particular cross section right there. So you can see in the curve that has the amplitudes extracted in this track here on the right. And we did the same thing for the Paradise machine learning lithofacies predicted payzone lithologies that we see here on the right in this cross section here. And then we also show a kind of a binary curve. So wherever you see green, that's basically where the well corresponded to the actual cutoffs that we use for both the amplitude as well as for the neurons in order to highlight the actual payzone. You can see the difference between the green here on the left and the green here on the right, that we are effectively predicting different payzone length thicknesses along the horizontal well. So we compared both of these and just analyzed it throughout the field to kind of see if we could see any patterns or trends. So extracting it along the lithofacies along the well for the vertical wells, you can see how we have the landward dipping ooid grainstones that we have identified successfully using the SOM, which we were able to generate using the mutual information workflow-based recommended seismic attributes. So that was very encouraging. We could basically properly characterize this landward stepping set of sequences of lithostratigraphic units. And then we could then compare it to the various vertical wells that we used as input for our lithofacies prediction. And then we could extract all of those predicted lithofacies here in the track here on the right along these horizontal wells. And here are just 3 examples of them. And then on the left, we could apply a little binary well between gray and green, a binary well log, I should say, that basically highlights what we would calculate as the payzone based upon the predicted lithofacies from Paradise. And then we started looking at individual wells, and this was a bit of a conundrum well, for instance, right? It was very well targeted in the low amplitude area, so we would have expected a lot from this well. Unfortunately, it had a very low overall cumulative production throughout its life. which was far less than the field average of about 120,000 barrels per well. So that was a bit of a mystery. So then we started comparing the actual overall thickness of the payzone from the amplitude analysis compared to the machine learning lithofacies prediction from Paradise, and we could see there was a distinct difference in the overall calculated horizontal well payzone length thickness. So we decided to then do that for all of the wells in the field to see if we could find a correlation between the amplitude-based payzone thickness and the lithofacies derived payzone thickness and the overall production performance of the various wells. And then cross-plotting both of those, we noticed that the machine learning derived Paradise lithofacies prediction, cumulative oil, correlated very well with the extracted payzone based upon the Paradise lithofacies cutoffs with an R squared of about 0.86. When we did the same thing for the amplitude cutoffs applied to the same horizontal wells for the same volume, we got the graph on the right, and this led us to conclude that we were able to validate the approach using the Paradise lithofacies prediction better than we could do with more traditional ways of developing this field, and that of course leads us to be encouraged by the approach, and took us to the next step of calculating the overall geobodies, for which we can then calculate individual volumetrics, right? And then continue to investigate how this approach using the Paradise lithofacies prediction can be used in not only this field but other fields in the Leonardian trends in the Permian Basin for the purpose of future field development, so important for the purpose of initial new initiatives like saltwater disposal, as well as CCUS operations, meaning potential additional enhanced oil recovery in the future. And also, perhaps, if possible, additional exploration and production initiatives. So once we extracted all the geobodies, we could then clearly show the contrast between the amplitude-based three-dimensional payzone delineation that you see right here, as well as the in red, as well as the yellow one, which was derived from our mutual information sourced self-organized map volume, cross-correlated with the lithofacies using the Paradise lithofacies prediction method. And we can see that there's a much better match between that lithofacies distribution and the overall analysis of the connectivity and the continuity of the payzone for the Kingdom Abo field. So that leads me to some conclusions. What we've learned from this exercise is that the Paradise machine learning lithofacies prediction workflow is very efficient and very useful for these sorts of detailed reservoir characterization projects. And what was an important objective of this particular study is to try the technique in areas with significant seismic and petrophysical challenges. So we're talking about older vintage seismic and very complex diagenetic overprint dolomite reservoirs, the bane of any carbonate geologist developing these challenging fields, to see if we could add any value to the understanding over the overall connectivity and continuity of the payzones. And as mentioned by the previous speakers, as well as Alvaro, the confusion matrix workflow is an ideal quantitative analysis tool. What we learned in this particular exercise is with the help of the machine learning team at Geophysical Insights, we were able to come up with a optimized workflow using mutual information methodologies to provide unexpected and valuable attribute selection recommendations for the final SOM analysis. And we hope that we're able to show you that we were able to validate the Paradise lithofacies prediction using individual well production performance data. And then my final comment is, as you can see, that this workflow showed a couple of Petrel pictures. That's one of the tools that we use here at the university in conjunction with many of our sponsor companies for our research consortia. And that is a very important link. The fact that we're able to directly move data from Paradise into Petrel and vice versa, and optimize these workflows as well as help with additional validation method. And you'll hear from other speakers in other presentations that there are that the other links, of course, are there for instance for tools such as the Kingdom SMT software from SMP. So what I found is that Paradise integrates very well with other tools, which makes it much easier to leverage its advanced machine learning workflows in our general reservoir characterization workflows. And that concludes my presentation. Thank you so much for your attention.
Okay, now we have the opportunity to address questions to all of our speakers, including Robin. I'd ask our speakers if they could come back in, and we will take, they will take any questions and respond to those now. Any questions of our speakers?
I have an observation for Robin. More than a question. Can you go back to your confusion matrix, Robin, please?
The one that I calculated following the mutual information network, right there. Yeah.
Yeah, that one right there. You know what I can see is that you have a lot of tight dolomite samples compared to the other, and I believe that's what is producing the very strong bias towards the tight dolomite. If I could share the screen that I showed again, Hal.
Before we do that, Alvaro, we do have a question. I just want to make sure we get to everyone's question if we can.
Yeah, sounds good.
Yeah, Gerardo asked, there are some reservoirs when we need more than to predict lithologies like geomechanics. Oops. Sorry, just lost the question. I think what the questioner is asking is, where does lithofacies apply versus inversion? That's probably a more general way of asking what's being asked here. If Robin, you could comment on it, and I would extend that question to our other presenters as well. Inversion certainly has a place. How would you, in what circumstances would you use lithofacies prediction in Paradise versus seismic inversion?
Yeah, well, we have much greater experts on inversion on this call, of course, that whose opinion I would want to hear on this subject as well. But as you saw from the first two talks where inversion was applied, it was the machine learning based lithofacies prediction method in Paradise was very favorably compared on a variety of comparative parameters, right? One thing I can tell you is that when we get around to publishing this particular work, I'll be able to touch more upon the unpublished inversion that we did, and it was a Bayesian inversion. And the results were not very good, mainly due to the challenging lithofacies. Right, the contrast between that it were just not strong enough for the inversion to really identify any sort of signals that would help in delineate the actual payzone. We'd hoped during that inversion process to maybe learn more about the karsting in the reservoir or any sort of fracture trends in there, right? Because we're dealing with this very strong diagenetic overprint, which had turned all the limestones into dolomite, which is makes for some wonderful reservoirs. But the most important thing for us was to try to identify where the high porosity, high oil saturation zones were located. And that's, I think, what we learned from this particular case study, is that we were able to do that much more successfully using the Paradise machine learning lithofacies prediction method than what we had learned from our traditional inversion workflow.
All right. And I did come back on to Gerardo's, the rest of his question. Let me restate it. There's some reservoirs when we need more than to predict lithofacies, we need geomechanic properties, as in not unconventionals. Have you tried something like that for conventionals?
Oh, that's so one of the things that I know and what I learned from this particular workflow is that when it gets to those sorts of geomechanical aspects, right, that is something that we would want to use the exact same workflow that we described in these three presentations that you saw here for in the future, in both conventional reservoirs as well as unconventional reservoirs. Absolutely.
All right. And I think this is probably a general question as well to all of our speakers. Ismael asked, how does this workflow handle the scale mismatch between well logs and seismic? And could the clustering, k-means, and SOM make this mismatch worse or introduce errors?
Hmm.
Alvaro, that may be a good one for you to take.
Yeah, I'll try to answer it. And yes, there is a difference in resolution many times in between. Let me go back to the question. Okay, between well logs and seismic. The well logs usually have higher resolution. What we do sometimes or should implement, permanently, is to take or to average the properties to one sample, the properties of the well to one sample. By doing that, we are removing that scale mismatch. And we have done that, and the metrics come considerably better. And as it does in here, and could the clustering k-means and SOM make this mismatch worse or introduce errors? The k-means, it would not introduce more errors than regular lithofacies created by cutoffs. I think it would create more or less the same. And again, the solution to that would be to upscale or to average the properties of the logs to match one sample of the seismic. And that we claim, or we have checked, or we have verified that we can identify one sample resolution. So that would take care of the mismatch. I hope that answers your question.
All right. And here's a question from Winita. How might this confusion matrix be presented to non-technical stakeholders to balance confidence with caution? And what threshold of false positives is acceptable in a development scenario versus exploration screening? Excellent question. Probably related as very much to business. Which of the speakers would like to take that one?
I can give my opinion
Yeah,
if you
go,
accept.
yeah, go ahead.
Yeah, okay. Yeah. How may this confusion matrix be presented to non-technical stakeholders to balance confidence with caution? We rely a lot on the on Kramer's value. So Kramer's value comes from from the confusion matrix, and that's a summary that is going to say, your predictions are strong predictions, or they are not strong. Usually, if we take as a threshold 0.4, when Kramer's V is higher than 0.4, we say that that is a good representation of the seismic lithofacies to the well log lithofacies. Now, what threshold of false positives is acceptable in a development scenario versus exploration screening? I cannot say exactly the values, but what I can say is that the false positives result in lower probabilities. So having the measure of probabilities is a good measure of what is acceptable. It's not right or wrong. It's how probable is it. If it's 50% probability, chances are that the prediction is not as reliable if it's 90% probability. I hope that answered your questions, Winita.
Yeah, also another good question. In most of the presentations, there was always the performance comparison with inversion results, which inversion scheme was used, such as the one presented by Dr. Marwa. Was it deterministic or stochastic? And how is uncertainty assessment in the predictions handled, such as equal probability realizations?
Good.
Marwa, you want to take that? Do you see the question in the chat? You are muted, Marwa.
Oh, sorry, I always forgot to unmute myself. Okay, so for simulation study, I used the pre-stack simultaneous inversion. I didn't use the stochastic inversion because, as you probably know, guys, the stochastic has many realization, and all of them has different probabilities. So we have different p's. So I was trying to find an inversion that gives me results similar to, I mean, I need probability volumes with most likely cases that I got from Bayesian inversion, which is similar to what I got from Paradise, where we have different probability for lithofacies and the most likely cases. So in this case, the comparison will go apple to apple. But if we try to do stochastic inversion, in this case, okay, I'm gonna have different probability volumes, different realization. So in this case, to which volumes I'm gonna compare to some. That's why they use stochastic inversion. What's the other part of the question, please? I think.
How is the uncertainty assessment in the predictions handled, such as equal probability realizations?
Okay, so here the assessment, we kept one well as a blind test, so I didn't conclude this in the presentation, but we kept one well as a test in both cases, and then we tried to visually assess the prediction ability of both methods, in addition to using confusion metric and Kramer's V too. So at the blind well, the results was reasonably good for both cases, but away from the wells, I think some gives us better results, or the unsupervised machine learning workflow gives us better results compared to the inversion.
Yeah, and I believe, Robin, you had 12 blind wells, was it, in your evaluation? So,
correct.
Yeah, that is a good method, and of course, for a robust testing of the model, leave one out, cross-validation is always a good method to apply. Another question, does it help to hyper-sample the seismic data prior to the Paradise workflow?
I can speak to that, and I think the answer is yes. We didn't show any slides of the differences, but there's a definite improvement in oversampling the seismic data in the lithofacies prediction, and I think that all of the speakers here could probably produce slides that confirm that, but we will most definitely ensure that makes it to the public domain. And the other thing that I wanted to hark back to is Alvaro's point of doing the proper sampling of comparisons in the Kramer's V calculations of the confusion matrices. That's something that I didn't get around to because it's a little time consuming, right? You could already see from some of my charts is that using different neuron topologies, you produce a different vertical resolution, inferred vertical resolution of your data. And then, of course, the best way to actually do the actual statistical calculation is that you have to equalize the sampling frequency and domain of the two parameters. So that's something that we can probably automate in some way, in which we can sample the well log data, as Alvaro suggested, to the actual vertical SOM resolution in order to come up with more appropriate Kramer's V calculations from those confusion matrices. Is that correct, Alvaro? when I put it that way?
Yeah, that's what I was trying to say as well.
All right. And Tom Smith has his hand up. Tom, you've made several good points in the chat. Would you like to add to those? You're welcome to unmute.
So it's not necessary.
Maybe, okay. All right. Any other questions of our speakers? Yeah, Danielle Pineda asked, what relationship do the distribution of final neurons have when using them in a cross graph as a variable? Does it have any physical relationship that can be related to any specific property?
So the advantage of like using the neurons or the trying to see how these neurons correlate with the different lithofacies and the transition zone, as we highlighted here, we just use a quantitative method called Coin heat map, trying to make assessment for the sensitivity of the legacy inverted porosity volume and the lithofacies prediction volume. That's why we use this quantitative method. And the result from that, we found that the lithofacies volume, the neurons themselves, highly correlated with the transition zone, which means they are highly sensitive to the transition between the lithofacies, if this answers the question.